It's day 5. We got some multiple choice questions for our questions of the day. So there's a complex number, a plus bi, plotted there. Okay, and what have we got to do? All the axes below have the same scale. The complex number minus I times a plus bi could be represented by which? So all we've done is we've taken this complex number here, and I'm going to draw its vector in. We've taken that vector there, and we're going to multiply. So instead of a plus bi, we're going to multiply it by minus I. Now we know that multiplying by I rotates by 90 degrees in the anti-clockwise direction. So rotating by minus I multiplying by minus I is going to rotate by 90 degrees clockwise. So we're going to end up down here-ish, somewhere down here. Also, if I multiplied that out, I'd be like minus AI and minus I times I, and I times I is minus 1, so plus B. So, you know, it's a long way out and then a little bit up, so it swaps over and it's minus A, right? Because A is this distance out to here, so you're going to go down minus A when you do your Y, because that's the Y coordinate, like X and IY. And B, it's only going to be a little bit out because B was only this little bit here, so B is going to be just a little bit out. So that point there is B and minus A, if that was A and B. So let's have a look which one matches. It's out of A and C, so it's got to be C. C is the answer there. One of the complex solutions to Z5 equals negative A, where A is a positive real constant, is A to the 5th cis pi on 5. One of the other solutions is a real number and is equal to, well, we know that all the roots are going to spread evenly around the complex plane, which is 360 degrees or 2 pi. So each of the 5 different roots are going to be 2 pi on 5 apart. So if this first one is at cis 2 pi on 5, then we're going to have A to the 5th pi on 5 is the first one. Then the next one around is cis. Now you've got to add 2 pi on 5 so that they're 2 pi on 5 apart. And then the next one is going to be cis 5 pi on 5, which looks like it's what we're after, but I'll just finish the explanation. The next one is cis 7 pi on 5. That's 1, 2, 3, 4. And the last one is cis 9 pi on 5. So this one here is saying A to the 5th cis pi. Now cis pi lands on the real axis, and that's because cis is cos pi plus I sine pi, right? So A to the 5th times that is A to the 5th times negative 1 plus I times 0, because sine pi is 0. So it's just negative A to the 5th. I mean, you could have seen that because that's an argument of pi around there. So B is the correct answer. All right, the region on the above Argand diagram where A is a real constant could be defined by what? Well, just generally, you'll have a circle if you've got Z minus some vector, I'll call it Zi, or Z1, say, equals R. That's a circle. Now, we've got the shaded bit inside the circle plus the actual outer edge of the circle. So we're looking at something of that nature. So this would be Z minus A plus 2I, because that's what that vector is. and it's less than or equal to some number. Well, it's less than or equal to the size of A, whatever that is. I say the size of A because they've been a bit sneaky here. Like, that's 2 up there, and it goes across here to this number A, but A is actually less than 0, isn't it? A is a negative number, and the radius can't be negative. But it's equal to that distance that you go to get out to A. That's the radius of the circle. Well, you know, it could be any number, but from their scale, it appears to be less than 2. It appears to be maybe 1. They've got 2 options here, which are possible, and the better of the options would be B, because I feel like that would be about 1 there. If it was 2, if it genuinely was 2, I guess because it's gone up 2, it should be touching down on the axis down there, and it's not. So 1 is the only actual option that it could possibly be. Which of the following relations does not have a graph that is a straight line passing through the origin? All right, I'm going to, for each of these, let z equal x plus iy. So, exploring part A, we've got x plus iy for z, and the conjugate of z is x minus iy. So, and that equals to 0. So that's 2x equals 0, so you get x equals 0. Now we know x equals 0 is just the y-axis. X equals 0 is this vertical line here. So that passes through the origin, like it says. It's a straight line passing through the origin. So that one's all right. Let's have a look at B. 3 real z, which is 3x, equals imaginary z, which is y. Well, that's the line y equals 3x, so it's something like that. Okay, let's have a look at C. Z, which is x plus iy, equals iz bar, I conjugate of z, which is x minus iy. So that's x plus iy equals ix minus I squared, so plus y. So I'll just move down to give myself a bit of room here. That's x minus I, x plus iy minus y equals 0. So I've got x minus y and minus x minus yi equals 0. So that's x minus y into 1 minus I equals 0. So if you solve that, that's x equals y. This is just a number. You know, even though it says 1 minus I, there's no pronumerals. You don't put that equal to 0. That's just a number. 1 minus I is a number, right? So x equals y. The x equals y is just the line that goes diagonally across the number plane. Yes, it goes through the origin. So we're getting right down to elimination territory here. I just need to scroll back up and see what else we got. Real z minus 2 imaginary z equals 0. Let's give that a go. So D, real z minus 2 imaginary z equals 0. So x minus 2y equals 0. That's actually y equals a half x. So, you know, that looks like something like that going through the origin. Yeah, that's all good. So by elimination, we know the answer is E is wrong, but let's just, like, you know, to humour me, let's have a look at it. Real z plus im z equals 1. That's x plus y equals 1. So that's like the line y equals minus x plus 1. Well, yeah, it is a line. It goes through 1. Whoops, that's not a minus. Get rid of that. It goes through 1 and it just runs. No, it doesn't. Oh, shocker, Barry Crocker. If it ran like that, that'd be a correct answer. No, it actually runs through 1 like that. So it is a straight line, but it doesn't go through the origin. So we know that the line that does not go through the origin is in fact that last one, because it says does not have a graph that passes through the origin. Okay, what's the next one? Using a suitable substitution. Okay, this is a reverse powers rule, like the derivative of the function in the brackets is just sitting in front of the brackets, which means it's a classic for the substitution u equals whatever's inside the brackets. Okay, so I'll just do u dx it first of all. That's 2x. So wherever I see 2x dx, I can throw a du in. That's nice to know. Wherever I see a u, I can throw x squared plus 1. When x is equal to, so our original one has terminals a and b, so let's just, when x is a, u is a squared plus 1, and when x is b, u is b squared plus 1. So our integral from a to b of x squared plus 1 to the 5 dx. Now, if I have 2x dx, I can replace it with du. So I'm going to put a 2 in there in order to do that, but that means I've got to whack a half out front. So we're ready to do our replacements here. Now that's equal to a half, the integral, instead of from a to b, since we're replacing it with u, substituting with u, we're going from a squared plus 1 to b squared plus 1. And then 2x dx is just du, and x squared plus 1 is u, and that's to the power of 5. So we're going to end up with a half, and then this is a sixth u to the sixth from a squared plus 1 to b squared plus 1. Now, have we got anything there already looking like that? Half integral from a squared plus 1 to b squared of u5 to u. That's correct. So I don't need to go any further. The only one that's a bit suspicious is this one. So something must go wrong in their algebra of that one. I'll just see this through. This is a 12th, and then it's b squared plus 1 to the 6th minus a squared plus 1 to the 6th. So there's a lot. You can't just expand that and say that's b to the 12 and a to the and 1 to the 6. You can't just do that. And that's, I think, what they're indicating that someone might do by mistake for part E in order to just get a 12b to the 6th minus the 12a to the 6th. So yeah, that's not going to be right. So we know that our actual answer after is C. Okay, the position vector of a particle at time t seconds, where t is positive, is given by that. What's the direction of motion? In which way is it moving? Well, that's the velocity vector. So we differentiate to get the velocity vector. The velocity vector, you just differentiate each of the directions individually with respect to t. So like that's minus 1, so it's just minus I. And that there will be a minus 6 times half times t to the minus a half, j, and that'll be 0 for 5k because it's just 5. So we've got minus I and minus 3 on root tj is what we need. And they're saying at 9. So v of 9 is minus I minus 3 on root 9j. Minus I minus 3 on 3, minus 1j. Yeah, so it's just minus I minus j. B is the correct answer there. So, oh, whoopsies, I didn't write j, I wrote I. Minus I minus j. And the thing to take away from there is you can just differentiate each direction there, like I, j and k separately to get the derivative vector. All right. That is question of the day 5.